This is a lecture for my Sem 4 student on quantum mechanics, and till now we have studied the basic postulates of the quantum mechanics, and today we would be dealing with time evolution of different functions like Schrodinger equation for non-relativistic particles, the first thing, and then we would deal with stationary states. So we know by now, according to the postulate, the last postulate, if we recapitulate, then there are two things to be remembered while dealing with the postulates of quantum mechanics. The first is the representation of the state, for which we have some four postulates, and the final one is the time evolution of the state, or how the time evolves, or the state evolves with respect to the time, and that is given by the Schrodinger equation. So we know by now that the Schrodinger equation is given by H psi is equal to IH cross del psi del t, where H is the Hamiltonian operator, H cap, psi is the state which actually represents a particular state. And if we want to write the Schrodinger equation for non-relativistic particles, so for non-relativistic particle, the starting point is the energy, which is given by p square by 2m plus v, which could be a function of r, where p is the momentum. So we can equivalently write the corresponding Hamiltonian operator as equal to p cap square by 2m plus v cap r. So this is something which is the language of quantum mechanics, in which we write the energy in normal dynamics language. The energy is given by the kinetic energy and the potential energy, and in the language of the quantum mechanics, the corresponding operator for the energy can be replaced by the Hamiltonian operator, and that is given by the momentum operator square by 2m plus vr. So we can write the corresponding Schrodinger equation as equal to E cap square by 2m plus v cap r operating on psi is equal to IH cross del psi del t. And we know by now from our previous class that P is basically equal to minus of IH cross del, because remember class in Px cap was minus IH cross del x, Py cap was minus IH cross del y, and Pz cap was minus IH cross del z. So P is this, so we can write this as minus of h cross square by 2m del square plus vr operating on psi gives us IH cross del psi del t. So this is the Schrodinger equation for non-relativistic particle. If one wants to see for relativistic particle, then the starting point would be for that. For relativistic particle, one can write E to be equal to root over of p square c square plus m naught square c4, and then we have something like Klein, and this would result in Klein-Gordon equation, and then to Dirac equation. So now we know the time-dependent Schrodinger equation, or the time evolution of the Schrodinger equation in exact form, which can be written as minus of h cross square by 2m grad square psi plus v r psi is equal to IH cross del psi del t. This is the time dependent Schrodinger equation. This is called TDSE, time dependent Schrodinger equation. Let us now talk about the stationary states, which was first enunciated by none other than Niels Bohr in the year 1913 to explain the hydrogen atom spectra. So what is stationary state? If we want to talk about stationary states, so we know that this particular equation is a standard equation like any other mathematical equation. This is a partial differential equation, and this is basically a function of r and function of time. So we can say that the solution to this is nothing but a function of r and t. And if we can use the method of separation of variables, then I can always write this to be equal to ur into f of t. If I say that this can be solved by the method of separation of variables. We know this method of separation of variables. Okay, so now if I use this over here, then I can always write this to be equal to minus of h cross square by 2mf. I'm eliminating the argument part. You remember f as a function of time and u as a function of r. So u is the spatial part and f is the time part, which is the solution to the above partial differential equation. So we can write h cross square f grad square u plus f vf into u, okay, is equal to ih cross u del f del t, and dividing both sides by uf as we do while solving by the method of separation of variables. What do we get? We get minus h cross square by 2m u grad square u plus v, okay, is equal to ih cross by f df dt. Okay, this should be d. Okay, so the left hand side is supposed to be a function of r only, and the right hand side is supposed to be a function of t only if v is only a function of r. So this would be some constant, you can say e, separation constant, if v is only equal to vr, there is no time part involved in the potential. So we can segregate the space part and the time part by the method of separation of variables by separation constant if and only if v is independent of time. Then we can very easily write the first part to be equal to okay, so the time part solving for f t, we can get df by f to be equal to minus of ie dt by h cross. So f is equal to some constant c to the power minus iet by h cross, and the space part is minus of h cross square by 2mu. solving for u cannot be done until and unless you know the value of v. So the space part, this was the time part, the above one was the time part. So grad square u plus v is equal to again e, and then we can write minus of h cross square by 2m grad square u plus vu is equal to eu. This is similar to what we had as Schrodinger equation in the first line, if you remember correctly. This is, and we can say that if we compare this equation with this equation, then we can say that E is nothing but equal to IH cross del del T. This is the energy operator. And this equation is again a Schrodinger equation. We have to solve this. This is called time independent Schrodinger equation. So this is another equation. We can solve it with the knowledge of time independent Schrodinger equation. Like TDSC, we have TISC, time independent Schrodinger equation. We will be solving this particular equation for different problems in our next section. There you would see how easily one can get different solution when the potential is time independent, and then you can solve this to get the value of UR. So this is going to give us the solution UR, which is the wave function, which is the space part of the wave function. So knowledge, we cannot go further beyond this particular line until and unless the knowledge of V is known, and this V must be time independent, as in real physical situation V is many a times time independent. For example, if you consider the potential in which an electron moves around a proton in a hydrogen atom, then the potential is given by minus of E square by 4 pi epsilon naught R, and there is no time part, and then we can always solve this and multiply it with this function, and we get the total wave function psi r t. Then we can get psi r t to be equal to C e to the power minus I e t by h cross into u r. So this is the solution, total solution of the wave equation. And one can always write, if one considers the principle of superposition, one can write it as a linear combination of different states. So by now we know that the solution of this equation is given by psi r t is equal to ur, and ft is nothing but c to the power minus of I e t by h cross. And if we have a linear combination of different wave function, then this can again be written as by the principle of superposition as un r cn e to the power minus en t by h cross summation over n. So any linear combination of different functions would be another possible solution to the second order linear differential equation, which is a property of the second order linear differential equation, which is the Schrodinger equation, time dependent Schrodinger equation. Now if we talk about the probability density, if I talk about the probability density, which is psi star psi d tau, then what we can say about this particular thing, we can always say that this is equal to summation over m comma n cm c and e to the power I e n minus em. Okay, take it minus I of em minus en. Okay, t by h cross. And if they are the same for m equal to n, this PRT is basically equal to summation, so that is going to give us a delta function, and we are left with something like cn square, which is a constant, and un square theta. So we can see that the probability density is time independent, and something which is time independent can be called as stationary. So this is the concept of stationary state. So if our potential is not a function of time, then the corresponding states could be stationary states, although they may have a time dependence, exponential time dependence. But whenever you take a complex conjugate, this I would cancel with minus plus of I, and they would cancel out to give you a probability density which is time independent, and that is the concept of stationary state, which was talked about by Niels Bohr. He said, according to his postulate, the orbits on which the electrons are revolving are stationary, that is, those particular states are independent of time. Since the potential is time independent, so the states would be time independent. The electron would revolve around on those orbits for infinite amount of time. They are not going to depend anyway on time. That is the concept of stationary states. Now, what about the expectation value of an operator? So if we now talk about the expectation value of an operator for stationary states. In this particular case, say I have an operator A. I want to find the expectation value for a normalized wave function. I can always write this as psi star A cap psi theta. Then I can always say that this psi is basically equal to some u star r e to the power I et by h cross a u r e to the power minus I et by h cross theta. Then we can again say that this is something which is u star r a u r theta. The expectation value can be seen to be again time independent. So for stationary states, the probability density, since the probability density itself is a time independent quantity, so is the expectation value. So that is the conclusion, that for stationary states the time evolution of the expectation value would be 0. So if one takes ddt of a operator, then that would be 0. So A is constant of motion. I hope that is quite clear by now. Thank you.